In quantum chromodynamics, QCD, color confinement, often simply called quark confinement, is the phenomenon that color-charged particles, such as quarks and gluons, cannot be isolated, and therefore cannot be directly observed in normal conditions below the Hagedorn temperature of approximately 2 trillion Kelvin, corresponding to energies of approximately 130 to 140 MeV per particle. Quarks and gluons must clump together to form hadrons. The two main types of hadrons are the mesons, one quark, one antiquark, and the baryons, three quarks. In addition, colorless glueballs formed only of gluons are also consistent with confinement, though difficult to identify experimentally. Quarks and gluons cannot be separated from their parent hadron without producing new hadrons. Origin. There is not yet an analytic proof of color confinement in any non-abelian gauge theory. The phenomenon can be understood qualitatively by noting that the force-carrying gluons of QCD have color charge, unlike the photons of quantum electrodynamics, QED, whereas the electric field between electrically charged particles decreases rapidly as those particles are separated. The gluon field between the pair of color charges forms a narrow flux tube, or string, between them. Because of this behavior of the gluon field, the strong force between the particles is constant regardless of their separation. Therefore, as two color charges are separated, at some point it becomes energetically favorable for a new quark-antiquark pair to appear, rather than extending the tube further. As a result of this, when quarks are produced in particle accelerators, instead of seeing the individual quarks in detectors, scientists see jets of many color-neutral particles, mesons and baryons, clustered together. This process is called hadronization, fragmentation, or string breaking. The confining phase is usually defined by the behavior of the action of the Wilson loop, which is simply the path in spacetime traced out by a quark-antiquark pair created at one point and annihilated at another point. In a non-confining theory, the action of such a loop is proportional to its perimeter. However, in a confining theory, the action of the loop is instead proportional to its area, since the area is proportional to the separation of the quark-antiquark pair. Free quarks are suppressed. Mesons are allowed in such a picture, since a loop containing another loop with the opposite orientation has only a small area between the two loops. Models exhibiting confinement. In addition to QCD in four spacetime dimensions, the two-dimensional Schwinger model also exhibits confinement. Compact abelian gauge theories also exhibit confinement in 2 and 3 spacetime dimensions. Confinement has recently been found in elementary excitations of magnetic systems called spinons. Models of fully screened quarks. Besides the quark confinement idea, there is a potential possibility that the color charge of quarks gets fully screened by the gluonic color surrounding the quark. Exact solutions of SU. 3. Classical Yang-Mills theory, which provide full screening by gluon fields of the color charge of a quark, have been found. However, such classical solutions do not take into account non-trivial properties of QCD vacuum. Therefore, the significance of such full gluonic screening solutions for a separated quark is not clear. QCD string. In quantum chromodynamics, or in the more general case of quantum gauge theories, if a connection which is color confining occurs, it is possible for string-like degrees of freedom called QCD strings or QCD flux tubes to form. These string-like excitations are responsible for the confinement of color charges since they are always attached to at least one string which exhibits tension. Their existence can be predicted from the dual-spin network, spin-foam models. This duality is exact over a lattice. To a surprisingly good approximation. These strings are described phenomenologically by the Polyakov action, making them non-critical strings. See also gluon field strength tensor, asymptotic freedom, center vortex, dual superconducting model, beta function, lattice gauge theory.